Hello and welcome back to Find, Solve, Explain. Today we're going to be doing the first question from the 2022 BMO2 paper. The question goes, a sequence A1, A2, A3, all the way on to infinity, has A1 is greater than 2 and satisfies an plus 1 equals an times, in brackets, an minus 1 all over 2 for all positive integers n. So, for which values of A1 are all the terms of the sequence odd integers? So, what I'm going to do is I'm going to assume that all of the terms of the sequence are in fact odd. So, we know that an is odd and an plus 1 is odd. So, let an equal 2r plus 1. So, where r is a real positive integer. Okay, then we know that an plus 1 equals 2r plus 1 times 2r all over 2. And that's congruent to 1 mod 2 because it's odd. So if we times everything by 2, we get that 4r squared plus 2r is congruent to 2 mod 4. And this gives us that r must be 1 mod 2 or odd. Okay, and therefore an must be congruent to 3 mod 4. Okay, now let an be congruent to 4r plus 3. This is not the same r, but I'm just going to keep r because it's kind of what I used. Okay, and then an plus 1 equals 4r plus 3 times 4r plus 2 all over 2, which is congruent to 3 mod 4. And we know that because an is congruent to 3 mod 4, an plus 1 must be. So, and then if we times everything by 2, we get that 16r squared plus 20r plus 6, which is the top of this fraction, is congruent to 6 mod 8. And then because this stuff is divisible by 8, we can remove it, and we can get rid of the 6's on both sides to give us 20r is congruent to 0 mod 8. And this means that r must be even, or is 0 mod 2. Okay, therefore an must be congruent to 3 mod 8. So we've just proved that an, if it's odd, must be congruent to 3 mod 4 and 3 mod 8. This kind of suggests that if this pattern were to continue, the only value that an could be is 3. In fact, if we know that an is congruent to 3 mod 2 to the x, where x is any real positive integer, we can prove that an equals 3 mod 2 to the x plus 1, which does suggest that the answer is actually 3. So I'm going to show you that proof now. So let an equal 2 to the x r plus 3. An plus 1 equals 2 to the x r plus 3 times 2 to the x r plus 2 all over 2, and is congruent to 3 mod 2 to the x. So multiplying both sides by 2, we get 2 to the 2x r squared plus 5 times 2 to the x r plus 6 is congruent to 6 mod 2 to the x plus 1. And this gives us, using the same thing we did before, 6 gets rid of that, and then this goes 5 times 2 to the xr is congruent to 0 mod 2 to the x plus 1. So R must be a multiple of 2, or even. So therefore an is congruent to 3 mod 2 to the x plus 1. So that means all of the values of the sequence are congruent to 3 mod 2, 3 mod 4, 3 mod 8, 3 mod 16, all the way up. So they're 3 mod 2 to the infinity. So the only possible solution for all of the values is 3. And so I'm suggesting that the sequence A1, A2, A3 continues as just 3, 3, 3, 3. And that's the only solution. And if you want to check that this works, you can put it back into the equation that we have from the question at the beginning. So an plus 2 equals an plus 1. Sorry, I don't know why I did an plus 2. Because an plus 1 minus 1 all over 2. So I'm saying that 3 equals 3 times 3 minus 1 over 2 equals 3. As you can see, that works. So the only solution for the value of A1 is 3. Okay, thank you.